If you were in middle school around 2014, you might be familiar with the sentence, some infinities are bigger than other infinities. But what does this actually mean mathematically? To understand the statement, let's look at the concept of sets. Sets are kind of a difficult term to define in math, and because of that, they're sort of one of the more vague concepts in math. But for our purposes, you can think of a set very intuitively as just a collection of things. These things can be numbers, letters, objects, words, ideas, or really any combination of those things. So for example, you could have a set that consists of the number 3, the tree in your backyard, and the concept of time. You can also have sets that contain other sets, and some sets are infinite. For example, the set of all real numbers. There are an infinite number of real numbers. Two sets are said to be the same size or have the same cardinality if there is a one-to-one correspondence between the two sets. For example, if we look at set A and B, we can see that each element in set A is matched with exactly one element of set B and vice versa. This one-to-one correspondence is called a bijection, and that means that these two sets are the same size. They have the same cardinality. On the other hand, if we compare set B with set C, we can see that not every element in set B can be matched to one in C because there's one left over here. So B and C are different sizes. This concept is pretty intuitive for finite sets because we can just count the number of elements. A and B each have 5 elements, so it makes sense that they're the same size, while C only has 4 elements and is therefore smaller than A and B. But to apply this concept to infinite sets, let's consider the set of all real numbers, which we call R, and the set of integers, which we call Z. Intuitively, you would expect R to be bigger than Z because the set of reals contains all of the integers as well as lots of other numbers that aren't integers. And you would be right. The cardinality of the reals is called the continuum, and the cardinality of the integers is called aleph naught. As it turns out, the continuum is greater than aleph naught, so there is no bijection between these two sets. This was proven by a mathematician named Georg Cantor in 1891 using a diagonal argument, which we will say for another day. So R is bigger than Z. The infinity of the reals is bigger than the infinity of integers. So now let's think about the set of integers Z and the set of even integers, which we'll call E. Both of these are infinite sets. Which would you expect to be bigger? Again, your instinct might be to say that Z is bigger because the integers includes all of the even integers as well as lots of other numbers, which are the odd integers. But as it turns out, the logic above doesn't really work for this case. These two sets are actually the same exact size. Remember that two sets have the same cardinality if there's a bijection, a one-to-one correspondence between them. Let's look at the function e equals 2z, where each z is an integer and each e is an even integer. So this function takes each integer and maps it to exactly one even integer, and there are none left over in either set. So this function is a bijection, and therefore these two sets have the same cardinality. This example is a simple yet important reminder that in the world of infinities, you really can't always function on instinct alone. Sets can work in surprising and counterintuitive ways. Not all infinities are created equal, and yet sometimes they are equal when you least expect it. Much of Cantor's work in set theory was shocking for his time, and people were very reluctant to accept his ideas at first due to his somewhat radical ideas about infinities. But you shouldn't let counterintuitivity scare you off like it might have scared off the people of Cantor's time. Often it is actually precisely the surprising nature of math that makes it so beautiful. And as Cantor says, the fear of infinity is a form of myopia that destroys the possibility of seeing the actual infinite.